All right, let's get started. So this is the second of two pre-recorded lectures that we're going to be doing in CE 414. This is going to be the lecture where we sort of fill in the gaps on a lot of the individual parameters related to tension member analysis. So when we get back, we're really able to just sort of hit the ground running on analyzing tension members and then ultimately designing them. So today we're going to be talking about two issues, one related to shear lag and one related to slenderness. Okay. Now, in order to set the stage, let's go back to some fundamental parameters which define what we do as structural engineers. And the first is the limit state, and particularly the LRFD limit state. So what we're dealing with is factored loads and factored resistances. So remember, on the load side, what we're doing is we're computing each of those individual load components and then we're factoring them, 1.4 dead, 1.2 dead plus 1.6 live, etc. And then we take the worst case factored load that we then compare against our factored resistance. Now, on the factored resistance side, what we do is we have nominal resistances, which are based on mechanics, the specifications, etc. We then adjust that resistance by an appropriate resistance factor, and we, are left with a factored resistance. And as long as the factored resistances are greater than the factored loads, the structure is safe. Okay. Now, what we're dealing with are tension members. Okay. So in tension members, first off, geometrically, we focus on two sections. We focus on the gross section and the net section. So the gross section is the main body of the tension member, basically the section of the tension member that is away from the connection region. And then the net region, or the net section, is the cross section that's through the connectors. Okay. Now, again, and I've said this before, but since the tension member is usually symmetric, we only really need to look at one side. We don't need to look at the other. And then remember, I had said earlier that the important section is the one that passes through the lead line of bolts. So we really didn't talk about that a lot in detail with grid-like connections. Obviously, that was very important with staggered connections. So hopefully by now, after our discussion of parallel bolted connections and staggered connections, we have a better understanding of what we mean by the lead line of bolts, and as well as just the gross section and the net section in general. Now, let's make sure that since that we're all on the same page, since we're discussing tension members, the section of the specification that is critical to us is the section on tension members, which is Chapter D of the spec. Okay. Now, if you open up the specification, so if you have your steel manual with you, open it up to page 16.1-28. This is Chapter D, the chapter on the design of members for tension. Okay. This is the section, the chapter that we're governed by. Okay. Now, it does have a note on slenderness limitations. We're gonna get to that in our lecture today, but for now, I'm gonna sort of go past that and go right into tensile strength. And so this is what the manual is telling us. This is how we compute the tensile strength of a member in tension. And so we have two limit states related purely to the tension member. We're going to add one later when we look at block shear. But for now, let's just consider these two strength limit states. We have the yielding in the gross section and the fracture in the net section. So if I wanted to compute the capacity of a member according to gross section yielding, I just take the gross area and multiply it by the yield stress. And that'll give me the nominal capacity, multiply it by a phi value of 0.9, and by golly gosh gee, I get the factored resistance. Okay. Now, the thing is, and let me go back to the slideshow here. If we go back to the slideshow, these are the same snapshots out of the manual. We have section D2 and we have section D3. There's one thing we have yet to talk about. For fracture in the net section, we have that we compute that capacity by taking the tensile stress and not multiplying it by the net area, but by the effective net area. And the effective net area, defined in section D3, is the net area adjusted by this shear lag factor. Okay, so let's just sort of take a step back and see where we are right now. Okay, so I have two limit states. Let's just sort of look at these expressions. I have 0.9 Fy Ag. Now, Fy and Fu, I can look that up in table 2-4 in the specification, right? So that's easy to find. I know how to compute gross area, and I know how to compute net area. So everything in these equations I can compute. So you would think we can go ahead and start analyzing and designing tension members right now. Hold on. there's one term left that we haven't talked about, and that's this term U. That's this shear lag factor. Okay, so what we're going to have to do is take some time and discuss that. Discuss what it means, what it is trying to capture, what it is trying to account for, and that takes some discussion. So let's get into that. So this term U is what's called a shear lag factor. Okay, and so what it's trying to account for is shear lag. So natural question is, what's that? What's shear lag? Okay, so one of the things that I mentioned when we were talking about staggered connections was that engineers sometimes have to deal with situations that are not easily accounted for by derivable equations. In other words, there is a difference between a mechanistic equation, something that you can derive like what we would find in structural analysis or mechanics of materials, versus something like an empirical expression that's more curve fit based on experimental data. Okay, now what happens in steel design is this. So oftentimes when we have a connection for a structural steel element, we don't connect all of the cross-sectional components. Okay, so what I mean by that is if I'm looking, let's say, at this this W section. Okay, this is a very common connection scenario. We have a W section and it is connected via the flanges. In other words, the web's not bolted to anything, just the flanges. Okay, so only some of the components are connected. Okay, now what that does is it creates a non-uniform stress region around the connection. In other words, if I'm yanking on this tension member, if I'm yanking on this W shape, I'm not yanking on the whole W shape, just the flanges. So I yank on the flanges. The flanges are the first component in that cross section to see the load. As you travel along the body of the member, it takes a while for those stresses to sort of catch up and distribute along the tension member, right? So this FEA stress contour that you see here on the right is a good example of that. So this is looking at the non-uniform stress region in a given tension member. So if you look here at the bottom here, you can see where everything's sort of a solid yellow. What that's sort of indicating is that the stresses in the gross section of the member are uniform, or at least uniform enough that we don't really need to consider non-uniform stress distribution. But when we're looking at, sometimes we're not just looking at the gross section, sometimes we're looking at the net section. And if you look at the net section, the stresses are all over the place. I mean, this is realistically what the stresses look like in a tension member when you yank on it, and they're weird. They're not uniform. They're hard to account for exactly. Okay, and so what we as engineers respond to that with is saying we're not going to handle it exactly. We're going to handle it empirically. Okay, if you wanted to handle it exactly, you'd have to do some really computationally intensive FEM. It's going to be time intensive. It's going to be costly. And there's really no point if you have a, again, good enough for government work solution. And I sometimes hate using that term because it sometimes cheapens the amount of hard work and time and labor that went into all the research necessary to define the data set and the factors that we use, because they do work very well. Their accuracy to simplicity ratio is excellent. So I don't want that good enough for government work term to just I feel bad saying that sometimes, but again, these factors work quite well. Okay, so what we're going to do to handle that is use what are called shear lag factors. Now, shear lag factors are in Chapter D of the manual. So, for example, if you go back to the specification, so let me go back to that. So this is Chapter D of the specification. So if you open your manual, this will be the first page in Chapter D. And then you turn the page and we get into the effective net area definition. This is where we define U and net area and U. But then when you turn the page past that, these are all the shear lag tables. Okay. This is definitely a guide in the manual that I would strongly suggest that you bookmark or tab, because you're going to be referencing this a lot in the analysis of tension members. Okay, now what this table lists is a series of cases that your tension member may or may not follow along. And then based on the given case, you have a formula for a shear lag factor that you can then employ. Now, the first thing I want to make clear is that it is possible that multiple cases may apply to a given connection. So in other words, you may be doing a problem and you might have case 2 as well as case 7 apply. So that is incredibly possible. Okay, so let's see. There we go. Okay, so the one case that I want to make sure that you're incredibly comfortable with is case 2. Okay, so I've copy and pasted the text from case 1 and case 2 into this slide here, because every tension member is theoretically going to apply to either case 1 or case 2. So if you read the definition, so if I go back to the previous slide, let me go back to the previous slide. If you go back to the previous slide, the text here is kind of small. So if you look at case 1 and case 2, it describes those cases. It's kind of small to read, so let's blow it up. Okay, so case 1 states if the load is transmitted to all of the cross-sectional elements by fasteners or welds, whereas case 2 says if the load is transmitted to some of the cross-sectional elements by fasteners or welds. So for the most part, except for a couple specific instances, tension members are going to fall under either case 1 or case 2. Now, if you're in a scenario with case 1 where all of the individual cross-sectional elements are connected, then U is 1. Now, let's remember what U does. What we're doing is we're taking the net area and we're adjusting it by U. And U is accounting for that non-uniform stress distribution. So if all of the components are connected, so going back to that example with the W section. So imagine I had a W section, but the web was connected as well. So all the flanges, all the webs, all the components are connected. In that case, we would fall under case 1 and U would be 1. But in most instances, we're going to have that the load is transmitted to some of the cross-sectional elements by fasteners or welds, in which case this is going to be our formula here. Now, that formula is formatted slightly differently than the table. So if you look at the table says 1 minus x bar over L. And instead, what I'm saying is 1 minus x bar sub CON divided by L sub CON. And I do that because I want to make sure that it's clear to you as the student what these terms represent, because they have very specific meanings. And case 2 applies to most tension members, so you really kind of need to make sure that you understand what's going on with case 2. So to explain case 2, I want to make sure that we're understanding what's going on with each of these terms. So case 2 says that the shear lag factor is 1 minus x bar over L. X bar is the connection eccentricity. Okay. Now the way that that's defined is it's defined as the distance from the connection or the connected face to the centroid of the member in question. So for example, if I'm looking at, let's say, this connection scenario right here. So I have an angle. It is one of the legs is connected, but the other is not. Again, that applies to case 2 because some of the elements are connected by fasteners or welds. So let's think about what's going on here. So there's more than likely going to be some plate or some member right here that it's connected to, right? So, that's where the bolts are going through, etc. So what is the connected face? This is the connected face right there. That's the connected face. Now it's an angle, so the centroid of that angle is probably somewhere like right there, so where that cross is. So the distance from the connected face to the centroid, that's x bar sub CON. Okay, that's what that term means. To be clear, with most problems in the manual, you can simply just look up the distance, but you just got to make sure that you're looking up the right term. Okay, that's incredibly important. As long as you're looking up the right value and using it appropriately, you shouldn't have a problem. Now, a couple things I want to point out. Okay, and I'm gonna actually open up the manual here. Okay, so let me open up the manual. So I've got here my AISC steel construction manual. Let's go to, let's see if that's a good page. I just made up a page, but there's a specific table I want to go to. Not quite. Actually, yeah, that's pretty good. That's pretty good. Okay, so let me zoom in a little bit so it's a little easy to see. Okay, So we're looking at WT shapes, okay? So for example, if you look at WT shapes, you can see that a couple things over here. So first off, now we're going to start to look over here at this side of the table. So if you notice, I don't have any centroid distances on the y-axis, but I do here on the x-axis, okay? The reason for that is this shape is symmetric, right? So if I look at a WT, right, I really only need to know where the centroid is up and down, right? I don't need to know where the centroid is left and right because I know where it is. It's right smack dab here in the middle. But up and down, I'm going to use one of these y-bar distances. Now I'm going to point something out right now. When you open your manual, you're going to see, if we look, for example, in the x-axis, you're going to see some instances where you see a y bar and then you see a y sub p, okay? For now, never use the y sub p, either the x sub p or the y sub p. Don't use it, okay? We will be able to explain what that means later in the semester. For now, all I'll tell you is that the x sub p and the y sub p terms are related to bending. We're not bending anything right now, we're just yanking on it. But as we get into flexure and beams, it'll be easier to explain what x sub p and y sub p is. For now, just steer clear of it. Okay, so let's get back to the presentation. So yeah, so make sure that you don't use the x sub p and y sub p. We'll look those values up later. But just make sure that you're using both the data in the manual and the schematics on the top right to ensure that you're using the right terms. Now, there is a very special case for the x-bar term, the x-bar connection. We're not going to deal with this today during this lecture or for the homework assignment, but we will deal with this during the next lecture. So whenever you have W sections that are connected via the flanges, what we do is we take that W section and we convert it to an equivalent WT. I know this might seem a little wonky, but again, these are empirical relationships. So, you know, there might be a little wonkiness, but in the end, their simplicity compared to their accuracy. So you sort of have to just marry yourself to the wonkiness, as it were. But if you want sort of a theoretical underpinning, the idea is that if I have a W section connected via the flanges, the idea is that as you apply load, half the load goes to the top portion of the member, half goes to the bottom. Hence why we take this W section and sort of convert it to an equivalent WT. And what we do is we take the Y bar from that equivalent WT, and that's the X bar sub CON. So while it's a little wonky to see, it's actually pretty easy to employ. So what you do is, let's say your tension member is a W12 by 30. What you would do is look up a WT 6 by 15, because half is deep and half is heavy, and just look up the equivalent Y bar, and then that's what you use. So again, while it's a little weird, it's actually pretty easy to employ. And we're going to have an example on this during the next lecture when we come back in person. Now, for the connection length is pretty easy to understand. I think what I'm going to do is play some OBS magic and move my camera over here. So whenever you're looking at connection length is defined for bolted connections as the out-to-out distance between the centers of bolts. So if you have a grid-like connection, it's pretty easy. But if you have a staggered connection, it's just the outermost bolt to outermost bolt. That's the connection length. For welded connections, it's the average length of the fillet weld along the direction in question. We won't really be dealing too much with welded connections now. We'll do that later. But one thing I will say is that this connection here might look a little strange. Like, why would you have one side welded longer than the other? There is a specific reason for that, and we will talk about that later. All right. Now, before we get into shear lag factors, I do want to take a second and talk about slenderness limitations or the lack thereof. Now, if you remember, I said I was going to go to the specification and sort of highlight what's going on with slenderness. Well, again, Chapter D covers tension members. So go to Section D.1, and here's what Section D.1 states related to slenderness. There is no maximum slenderness limit for members in tension. Okay? So some of you might be thinking, well, why are we talking about it? Okay, well, there's a couple reasons why we're talking about it. First off, just because there isn't an actual maximum slenderness limit does not mean that there isn't one you shouldn't employ. And the manual even says that. It says for members designed on the basis of tension, the slenderness ratio preferably should not exceed 300. And there are good reasons for that. If your member gets very, very slender, you can get some damage during shipping. It can be difficult to erect. You can have excessive sag. It can cause the structure to vibrate too much. It can deflect a bit under its own self-weight. So just because the manual doesn't make you follow slenderness limits doesn't mean that you shouldn't. I mean, you should. In general, there are limits in the spec which may not be directly codified like this, but you should employ. So in this class, we are going to employ slenderness limits for all of our designs, except for threaded rods, but we'll get to that later. Now, I should also say that slenderness limits this is our first service limit state. So it's not about structural safety, it's about day-to-day performance. So you'll notice you really won't see factored loads have anything to do with this. All we have to ensure is that this member's slenderness is limited to 300. Now, how do we define the slenderness of a member? Well, we define the slenderness of a member as the length of the member divided by its radius of gyration. Now, if you've forgotten what the radius of gyration is, the radius of gyration is the square root of I over A, I being the moment of inertia and A being the area. So the reason why we like using R, so R, if you want a simple definition of what R is, so if you remember, the moment of inertia is it is a quantity that describes how stiff a cross section is when being bent, right? So if you've had me for engineering 216, one of the examples that I use is if you've got 2x12s and you're trying to stand those up as floor joists for, let's say, a roof deck or your back porch. Those floor beams are going to be oriented like this, not like this, because whenever you're taking a 2x12 and you're bending it, it's just stiffer that one way than it is the weak side. And that's because the moment of inertia is larger along that axis than it is along its weak axis. In fact, the terms strong and weak axis are something we're going to be referencing quite a bit in this class. So a little bit more OBS magic moving my camera up here. So if you're ever looking at slenderness, so first off, one of the first things that I like to do in class is whenever we're talking about slenderness, sometimes it's a little difficult to try and maybe put a try and take slenderness and apply a geometrical understanding of it. So I've got some examples. So for example, if you had a Campbell's soup can, its slenderness is about 6. So if you take the length of the soup can divided by the radius of gyration of that circle, L over R is about 6. If we're talking about, let's say, a AAA battery, it's about 17. For a dry spaghetti noodle, so right out of the Barilla pasta box, the L over R, a spaghetti noodle is very slender, so it's about an L over R of 500. For Slender Man, who knows? But the mathematical term for computing slenderness is L over R, the radius of gyration. If the moment of inertia is a measure of how stiff an element is along one axis, the radius of gyration is too. What the radius of gyration is, though, is just the moment of inertia scaled down so that it's expressed in inches. Remember, moments of inertia are in inches to the fourth. So if you take a moment of inertia, divide it by an area, and then take the square root, you get an answer in inches. Now, one thing that you got to be careful about, let me go back to my presentation here. One thing you got to be careful about when computing slenderness is you got to be real careful on the units, okay? Because when you look up the radius of gyration will typically be in inches. But then if we're talking about how long a member is, we typically express that in feet. Well, you have to ensure that your units are consistent. L over R is a slenderness term, and slenderness terms are dimensionless. They are unitless. Now, what I'll tell you right now is that slenderness for us in tension member land is just going to sort of be a check that we do on some of the problems that we are analyzing. But when we get into columns, slenderness is going to be very important in understanding a section's capacity under buckling, under both strong axis buckling and weak axis buckling. So that's going to be, we're going to have to pay attention to slenderness in much more detail than we are right now. It's not to say it isn't important, but our addressing slenderness is going to be much more simple here. All right, so what we're going to do is we're going to look at an example, and let me pull up the notebook in the class, and play one more rearrange game for my camera, is we're going to determine the shear lag values for these two shapes, okay? So I've got a C10 by 30 and I've got an L8 by 8 by 5/8. So we're going to determine the shear lag factors for these two elements, and we're also going to determine whether or not the section meets slenderness limits if the channel is 15 feet long, okay? So let's get into this, and because those images were a little small, I decided to copy that image over a bit. Actually, I'm going to take this, I'm going to keep this minimized because we're going to be probably hopping back and forth between some screens here. Okay, so the first shape that we're going to have is a C10 by 30. Okay, so in order to compute the shear lag factor, the first thing that we need to do is we need to be a little cautious on where did my mouse go? Sorry. When you have that many monitors, sometimes it's hard to kind of see where your mouse pointer is. Okay, so here's the shape that we're going to look at. So the first thing that we need to do is we need to identify which shear lag factors are applicable, which cases are applicable for this element. Okay, so we have a C10 by 30 or a channel, and it is connected via the web. But notice how the flanges on the top and bottom are not connected. Okay, so that's very important. So let's go back to the steel manual. So we're in page 16.1-30. Okay, and give me one second. I'm going to get my pencil here because I want to make sure that we are denoting which cases are applicable. Okay, so the easiest thing to do is to just go through each of these cases one by one. Okay, so case 1. All tension members where the load is transmitted to each of the cross-sectional elements by fasteners or welds. That's not the case for this problem because the flanges aren't connected, just the web. So if the question is, does case 1 or case 2 apply? Case 1 does not, but case 2 definitely does. So we know we're going to have to apply case 2. What about any of the others? What about case 3? Do we have to apply case 3? All tension members where the tension load is transmitted by welds? No, don't have to worry about case 3. Let's see. Case 4, plates, angles, channels with welds at heels, C's. Okay, we don't have to worry about case 4. Case 5, HSS. No. Case 6. No. Case 7 and case 8. Case 7, WMS or HP shapes or T's cut from these shapes. No. Case 8, single and double angles. No. So the only case that we have to worry about for this member is case 2. And what you're going to find with tension members more often than not is it's either case 2 or case 2 and something else. So what we'll do is we'll say cases 2 only. All right. And so case 2, U2 is 1 minus X bar over L sub CON. Okay, so L sub CON is easy, okay, because L sub CON is the distance from the outside bolt to the outside bolt. So what is this dimension here? Well, it's 369 inches. So L sub CON is 9 inches. That's easy, okay? So what about X bar sub CON? Well, X bar is the distance from the connected face to the centroid, okay? Remember that in the case of, X bar, we're looking at whichever face of the section is connected, so that back face of the channel, and if the centroid is, I don't know, let's say right here, then this is the dimension that we're looking for. We're looking for this dimension right here. That's X bar sub CON. That's the dimension that we're interested in, okay? So what do? We open up the manual. So here's the manual. Let's go to, we're going to have to go back a little bit. Channels are in table 1-5. Let's see how my memory is. Maybe page 1-42. I was one page ahead. Let's try. Okay, so I think maybe 1-38. Yeah, here we go. Okay, so I'm in table 1-5, okay, and so this is the table on C-shapes. So let's zoom in a little bit so you all can kind of see what's going on. Okay. So first thing we want to do is we want to look at our schematic up here to make sure that we're really kind of understanding what's going on. So this is our schematic for channels, okay? And what we're seeing here is we're trying to get from the connected face to the centroid, and that's this term X bar. Remember, we look up X bar, we do not look up XP, so ignore the XPs, okay? So we're looking at C10/30, so this is the C10/30, and I'm going to try and just drag horizontally, okay? One of the things that you'll see on the right page is if you look right here, I don't know if you can see my mouse pointer there, but if you see the 30, okay, you can see that that you can follow along with the weight. So see on the very first top rows on the page, it says 50, 40, 33.9. Over here it says 50, 40, 33.9. So it helps you as the user identify what row you're on. So we're going to go to the 30. So here's the line 30. So you can see we're on the row that's right on the top of my camera. And so we go to X bar, and X bar is 0.649. Okay, 0.649. So what I can do now is I can go back to OneNote over here, and I can say, oh, let me. So we'll say X bar sub CON. It equals X bar for the C10/30, which is 0.649. So the shear lag factor is pretty easy to determine. So what we'll do is we'll just say U equals U2, which equals, and I didn't have this one computed, so we'll do this right here. And we'll say 0.928. And so there you go. Now, shear lag factors are always going to be less than or equal to 1. Because what they're doing, what their intended purpose is to take the net area and ask how much of that area is effective in transferring stress. So if you think about it that way, the answer is either all of the area or some of the area. So it has to be less than or equal to 1. So if you're doing the math and you get something bigger than 1, you're doing something wrong. So you probably have a calculator error in there somewhere, something like that. Okay, so now let's look at our next shape. So our next shape is an L 8 by 8 by 5/8. Okay, I can do that first 8 a little better. That's going to bug me. Okay. So we're going to do the same thing here. Is we're going to ask ourselves which cases apply. So I'm going to go to the specification, and I'm going to do the same thing I did a little bit ago, but I'm going to just go through it again. Okay. Now let's make sure that let's go back to the connection. I know I'm hopping around a little bit, but let's make sure that we look at the connection. So here's the member. Okay. It's an angle, and only one of the legs is connected, not both of them. So therefore I know that case 1 does not apply, but I know case 2 does. So let's go through it again. Does case 3 apply? No, case 3 has to do with welds. Does case 4 apply? No, it has to do with welds. 5 and 6 are both HSS. In case I haven't said it before, HSS stands for hollow structural sections. So we're talking about pipes and tubes and things like that. So doesn't apply there. What about 7? WMS or HP shapes or T's cut from these shapes? No, does not apply. What about 8? Well, hold on. Single and double angles. Well, that does apply. So now we have case 8 to consider. Okay. Let's go back to that. Okay, so I'm going to pull this over here. Let's see what happens there. Okay, so let's see what happens. I'm going to pull my manual over here, and so we might screenshot that a little later. But now we have a couple cases to consider. We have case 2 and case 8. Interesting. So let's take each case one at a time. All right. Just like last time, the connection length is pretty easy to find. Now remember, whenever determining connection length is from the outer bolt to the outer bolt. So we're talking about this distance right here. So that is LCON. Now what is LCON? Let's see. So it's 2, 4, 6, 8, 10. 10 inches. Okay. So just make sure that you're being diligent on that and that you're being detailed there. Sometimes, like, it's easy to fall into the trap where, well, the bolts are spaced 2 inches apart and there's 6 bolts, so it's 12. Now, 6 bolts means 5 spaces, so just make sure that you're following along with that. Now, what about X bar? Okay, well, again, just like before, we're going from the connected face, which case that's going to be over here. So if that's the centroid, that's X bar sub CON. Okay, so now let's go back to the manual. Let's see what we can find here. So let's see how good I am at predicting page numbers. I think it's probably like 1-44. Hey, look at that. Pretty good. Okay. So we're looking at an L8 by 8 by, what was the thickness? Sorry. I should have had that memorized. I did not. 8 by 5/8. It's an L8 by 8 by 5/8. So we're going to go up here a little bit. L8 by 8 by 5/8. There we go. So we're on this row right here. Now, first off, again, look at your schematic. So one of the things to keep in mind is that if you ever have an angle of unequal length, unequal leg length, X bar measures from the long leg to the centroid and Y bar measures from the short leg to the centroid. But we're lucky on this problem because we have an angle that is of equal leg length. So for example, if you look at the L by 8 by 8 by 5/8, look at the Y bar. The Y bar is 2.48 inches, but if you look at the X bar is also, or sorry, no, 2.21 inches. I was looking at the R column. See, you got to be diligent there. So yeah, so the X bar in this case is 2.21 inches. It's also the Y bar is 2.21 inches as well. Again, because it's symmetric. If it wasn't symmetric, then that wouldn't be the case. Okay, so make sure that you are being diligent on looking at the right column. But again, if it's an equal leg angle, it doesn't matter. So we're looking at 2.21 inches. Okay, so we can go back here to our manual here. We can say 2.21 inches. So therefore, U2 is 1 minus 2.21 inches over 10 inches. And so when I check that out, I'm getting 0.779. Okay. Now that's U2, but that's not U8. Okay. So what's going on with U8? Well, to make this easy, I'm just going to copy the section in the spec directly from the manual so that we don't have to keep back and forthing. So bear with me. Once this snipping tool decides to load up. There we go. That's a little easier. All right. So let's make that a little smaller so we can kind of see everything. Okay. So what we've got here is we've got the section in the spec. Now let's read that somewhat diligently to make sure that we're all kind of on the same page. So single and double angles, does that apply? Yes. Okay. Now, once we're in case 8, we have 2 paths that we can go to. So we have 4 or more fasteners in the direction per line, or 3 fasteners per line. Now, when we say per line means in the direction of loading. So if we are loading, this way, then the line is this way. So for each line, so for this connection, we have 2 lines, and each line has 1, 2, 3, 1, 2, 3 per line, and the line are in the direction of loading. So what I say is we're right here, so 3 fasteners per line. So we have single and double angles. We have 3 fasteners per line in the direction of loading, and so because we are dealing with a single angle, we have 3 fasteners per line. That's our U value. So U8 is 0.60. Now, there's 2 shear lag factors. Which one do we use? Okay. Well, read this right here. If U is calculated per case 2, the larger value is permitted to be used. Okay, and what that's essentially saying is that, remember, again, these are empirical. Okay, they are simple but accurate, but every now and then you got to curve fit that expression. Okay, and what the spec is saying is that if you computed per case 2, you could go ahead and use that one, and that one's the one that you're permitted to use from a capacity standpoint. So what we're going to do in those instances is say that U, because we're using the larger value, is U2. And so that's going to be our response. That is, that sometimes can feel maybe, I don't know, maybe a bit icky to a structural engineer that, wait, aren't we supposed to use the most conservative value? Yes, but keep in mind that you're also trying to use the value that maps the behavior as best as possible. And what the spec is saying is that this maps the behavior as best as possible, so you can go ahead and use that. I mean, keep in mind, you are taking that that angle and reducing its net area by over 20% based on this shear lag factor. So I mean, you are doing quite a bit to it you are doing quite a bit of reduction from a capacity standpoint already. Not to mention safety factors and load factors and things like that. Okay, now we got one other part of this problem. This part's kind of new, so I'm gonna scroll up kind of at the very beginning. Also, does this channel meet the suggested slenderness limits if it is 15 feet long? So we're going to go back to the C 10 by 30 and ask about its slenderness limits. Okay, so channel slenderness check. Okay, so we're looking at the C 10 by 30. Okay, now what the spec says is that L over R, in this case R minimum, has to be less than or equal to 300. And I guess I guess that's not really a fair way of saying it. The spec actually doesn't have a codified slenderness limit, but it has a very strong suggestion that this is your maximum slenderness. That's what we're going to employ in this class, and that's what most structural engineers employ as well. Now, we're going to need to look up some parameters for the C10 by 30. I'm going to do that here in a second, but I'm also going to look at the length right now. We were given that the channel length was 15 feet. Before you do anything, convert that to inches. Multiply that by 12. Because the radii of gyration that we're going to be looking up, they are in inches. Okay, so make sure that you're looking up the appropriate values. Okay, now let's go back to the manual again. And once it goes to the page in question. All right, so we're at the C10 by 30. So here's the shape, C10 by 30. And we're going to be looking at the RX and the RY. Okay. So for the shape in question, we have RX and RY. So let's see if we can write this down. So we're at the C10 by 30. We got the RX is 3.43. The RY is 0.668. Okay, so let's put that down here on our notes. So, too many monitors. Okay, so we were given that RX is, or we looked up the RX is 3.43 inches, RY 0.668 inches. So we use R minimum. So therefore, we get that. Let's see what we get. That's going to be close. Oh, 269.5. We'll just say 5 there. So does this member meet slenderness limitations? Yes. Okay. So what we will do in some of our calculations is we'll say something over here on the side that this is like less than 300. And so what you'll see me write is something like the slenderness is less than 300, therefore okay. If it doesn't work, you might see me write therefore NG for no good. So you'll start to see me do that in some of our calculations later on. So as that shows up, that's sort of what that means. So what's the answer? Channel meets slenderness limits. And that's it. So pretty straightforward. Hopefully you found that this lecture was really, I mean, the two problems that we're looking at, shear lag and slenderness, are really not all that complicated. They're really pretty easy to handle. I do want to make sure that I am giving a brief discussion on the homework assignment. So the homework assignment looks at the same angle, and you have two different questions on it. So the first one is what is the shear lag factor for this angle, and then what is the maximum permissible length of the angle if applying slenderness limits of L over 300. Now, one hint I will give you on the second problem is that you want to be very, very careful when you're selecting the appropriate R value for the angle. So what I mean by that is for angles, you will find both an RX, an RY, and an RZ. An RZ based on the principal axis. So just make sure that you're using the right one. Again, we're always using the minimum for slenderness checks. Again, same scenarios before. Just go through the shear lag table, find the ones that apply it to this, and hopefully this assignment should be very, very quick. With that, that's all I have, and I will see you all when we get back on Wednesday.